Hello, AP Physics C students. Let's talk a little bit about energy density. We'll specifically be looking at the energy density of a parallel plate capacitor, but it'll be applicable to anything. Now, we have three different equations for the energy stored in a capacitor. We're just going to choose one of them. Specifically, we're going to look at this one here. The potential energy stored in a capacitor is 1/2 C delta V squared. Okay, and we're just going to play with the equations a little bit and see what we can get. So we are specifically talking about parallel plate capacitor, and what's the most generic version for the capacitance there that we just described recently in class? Yeah, it's the one involving kappa. So it's this, that C equals kappa epsilon naught A over D, where kappa is this dielectric constant for the supporting insulating material between the conducting surfaces. We can condense kappa epsilon naught into just epsilon. Right, epsilon is just the permittivity of whatever material is there between the surfaces, whereas epsilon naught is assuming it is specifically vacuum or air supporting it. Okay. What about delta V? Well, oppositely charged capacitor is really just oppositely charged parallel plates, and we have an equation for the delta V, the potential difference across them in terms of the field. We've used it plenty of times. Delta V equals ED. All we're going to do is just take each of these equations and substitute into the master equation for energy stored in the capacitor. So C is going to become epsilon naught A over D, delta V is going to become ED. We're just going to square both those terms. I hope you're okay with that, right? So it's E squared D squared. All right. Obviously, one factor of D goes away. And so we're left with this, 1/2 epsilon E squared times A times the remaining factor of D. And I group these together in this particular way because over here we have A times D. That's the area of one of the plates of the capacitor, times D, the distance of separation. You might say, wonder if we could replace that with anything. What is A times D equal to? Well, just in case you're having trouble visualizing it, here's our parallel plate capacitor, where A is, the area of one of these plates, and D is the distance of separation. I think you should be able to tell me A times D is, yeah, it's the volume of whatever is in between the plates. So it's a volume. Again, we're assuming it's parallel plates, but this derivation will be generic for anything. So I can replace AD with volume. Okay, so now we can talk about this idea of energy density, which is like the concentration of energy, which we will define as energy divided by volume, right? Just like any other density, something divided by, in this case, the space it takes up. So what is this energy density? Well, we talked about in class, how actual capacitors are formed by rolling up those long strips of metal, which are separated by some sort of supporting insulating material, into as small a device as possible. But no matter how small it is, those capacitors do take up some sort of space in the circuit. And so you can think of this energy density as sort of an efficiency of space. That the more densely packed the energy is in a certain volume, the more efficient that capacitor is when space is at a premium. All right, so all we do is then take this equation, divide by AD, which of course is the volume, and we're left with this term 1/2 epsilon E squared, where epsilon is the permittivity of the material, supporting material separating the capacitive surfaces. We'll just go ahead and box this whole thing in. Normally we'd say, what's the symbol for energy density? Well, as it turns out, there isn't really an accepted energy density symbol. I've seen a couple of attempts at using one, but doesn't seem very standard. So it's just literally written out as energy density, or UC over volume, and it's equal in this case to 1/2 epsilon E squared. Now, I'll be very honest, we don't tend to use this idea of energy density very often, but here it is for when we need it.